Back in the 17th century, at a time we call the Middle Ages, a bubonic plague swept through Europe. They called it the Black Death. Children made up songs about it as a way to handle the horror. Before it was over, it had killed millions. Then, in the early 20th century, as thousands of immigrants swarmed into America, another calamitous epidemic struck. This time, it had a more scientific name. They called it tuberculosis. Nonetheless, before it was through, it too had slaughtered thousands. Today, with all our advances in modern medicine, we still seem to be helpless against the onslaught of infectious diseases. This time, the enemy is AIDS. Of what help can mathematics be against such a killer? That's what you'll discover as we develop a model for tracking a killer. In the fight against infectious disease, doctors must find answers to a whole host of questions. How many might contract the disease? How quickly might it spread? At what rate might we reduce its spread? And at what rate might this reduction control the epidemic? If we can develop a serum, how much might we have to stock? Because the rate at which a typical infectious disease spreads varies with time, calculus can play a significant role in helping health officials deal with the problem. Using calculus, it is possible to create a mathematical model that will help answer some of these questions. We'll start by solving a simple problem, then try and improve our model. Assume the Department of Health has gathered for us some basic data that describes how a typical infectious disease might spread. Let's use it to develop a model. The vertical axis, I of T, represents the number of people infected. The horizontal axis, T, represents the amount of time that has passed in days. Notice that if we look only at the first few days, it appears to resemble an exponential curve. Later on, there's a period of steady increase until the spread levels off. Let's say the number of people infected at time t plus 1, I of t plus 1, is equal to the number of people infected at time t, I of t, plus the change during one time period, ki of t, where k is the infection rate. Here, ki of t represents the number of newly infected individuals during a given time period. Let's rewrite the equation so it now looks like this. This difference equation has a solution, and here it is. I of t, the number of infecteds at time t, is equal to some arbitrary constant, c, times the quantity 1 plus k to the t. Furthermore, if our epidemic begins with one infected person, then I at time 0 is 1, so c is equal to 1. Putting it all together, we get that I of t equals 1 plus k raised to the power of t. Let's look again at our early data. As you see, it looks somewhat like a graph of 2 to the t. Substituting a value of 1 for k in our equation, we get the following results. A graph of 2 to the t versus the data allows us to compare our results and find out, does our model work? Well, for the first few days, it looks pretty good. But as time goes on, the answer becomes obviously no. As we know, 2 raised to the power of t grows very quickly, so it cannot adequately model the long-term spread of this epidemic. And the fact that plagues have not wiped out all life on our planet is further proof that an epidemic will not wipe out the entire population, as these results imply. No matter, that's what modeling is about: making assumptions, trying them out, and improving them if you can. Okay, let's move on, this time to the case of the red eye virus.
The mysterious red eye virus has reached epidemic proportions, say health department officials, as the disease sweeps across the city. The death toll now stands at 112.
Councilman Kraler dead. I can't believe it. He was here 3 days ago. Looks sick.
Hey, Barney, maybe it's this beanery food of yours.
Beanery food, this home cooking.
I've been waiting 15 minutes for a tuna sandwich.
Sorry. Hey, Charlene.
This epidemic began when an infected girl by the name of Charlene came to work in a small, relatively isolated community. It is spread by personal contact between infected and susceptible parties. No one had the disease before, and therefore no one is immune. Keep in mind that we know for sure that many, but not everyone, will catch this disease. Once again, here's our data. Now let's see if we can create a model that gets us a little closer to realistically describing the behavior of our contagious disease. Now let's say that I of t plus 1 is equal to I of t, as before, plus the product of the infection rate k, the number of infecteds I of t, and the number of susceptibles S of t. Since our population is relatively isolated, I of t plus S of t is equal to a constant, say 40,000. So S of t therefore equals 40,000 minus I of t. Putting this into the difference equation gives us this. Unlike our previous model, we cannot find an explicit solution to this problem. It is a nonlinear difference equation. However, we can iterate through the system, noting that different values of k for different infection rates would increase or decrease the values of I at time t plus 1. Let's plot the results of our model. Note that the shape of our curve looks right. However, it begins to level off at 40,000, and since that's our total population, the results of this model imply that everyone gets the disease. Intuitively, we know that's wrong. So let's try again. This time, we'll use calculus to test this model by changing our nonlinear difference equation to a nonlinear differential equation. We do this by changing the time period. With some rearrangement, this expression can be written as: we now take the limit as delta t approaches 0. The left-hand side is the derivative of I with respect to t, and the right-hand side is unaffected. So we now have di dt is equal to the infection rate k times the number of infecteds times the number of susceptibles. As before, our population is constant, so I of t plus S of t equals 40,000. S of t equals this. Substituting for S in the previous equation, we get the following. Recall that the initial number of infecteds is 1, so with some effort, the calculus student can solve this differential equation and arrive at this solution. Notice that as t gets bigger, e to the minus 40,000 kt goes to 0, and I of t approaches 40,000 as before. So the bad news is that our model is not accurate. But the good news is that we now have a continuous model and we've applied the calculus to it.
Doctor, the report on the cat, it's positive.
I want that diner closed now.
You can tell Barney yourself, he was just admitted.
Before time runs out, let's try again, this time with differential equations. Our first assumption is that di dt, the rate of change in the number of infecteds, is proportional to the number who are currently infected, or minus Ri, where R, our proportionality constant, represents the removal rate. Our second assumption is that ds dt, the rate of change in the number of susceptibles, is proportional to the product of those currently susceptible, S, and those currently infected, I. Both of these are reasonable assumptions. Assuming that I at time 0 is equal to I naught, some initial number of infecteds, let's solve the problem. We first solve for I of t in this differential equation and get the following. With I at time 0 equal to I naught, c equals I naught. We then get the following result for I of t. Substituting for I of t in the differential equation for s, we obtain this differential equation. This differential equation has a solution, and with some work, you should obtain this, assuming that I of 0 is 1. Notice that as t goes to infinity, e to the minus rt approaches 0. So our solution s approaches s of 0 times e to the minus k over r. Finally, we now see that how the disease runs its course is dependent on the ratio of k over r. We want the number of susceptibles, or S, to be as large as possible, and the number of infecteds, I, to be as small as possible. We do this by making k over r as small as possible. How can we do this? By somehow reducing the infection rate k, or increasing r, the rate at which the infecteds are removed from the population. Notice on this graph that as r increases in relation to k, the total number of people who catch this disease decreases. At last, our model begins to match our intuition about what the real world is like, and we can use it to make real-world decisions, like in the case of AIDS. What were some of our earlier questions? How many people will contract this disease? How quickly will it spread? Can we reduce its spread? Consider this. It takes about 7 to 10 years before the disease becomes known. If the relative ratio of infection rate to removal rate is, say, 100, where does that put us on this graph? Right at the top. Knowing and then influencing K, R, or both might then allow us to decrease the eventual number of AIDS victims. So health officials might seek ways to decrease K or increase R. By using calculus to track and model this killer, health officials might begin to answer some of the questions posed above, and one day find a model for its cure.
Thank you.